In this video, I will show you how to package a Spring Boot application as a Docker container. When we get to the deployment part of this tutorial, we will learn how to deploy our containerized Spring Boot application to the cloud. If you're not familiar with containerization, here is a little background of why we need this technology. Do you have this "it works on my machine" moment when deploying an application to a production environment? To develop an application, a developer needs to properly set up the development environment on her machine. But if the production environment is different from the development environment, the application will not run properly. In the production environment, maybe the JRE, Java runtime, is different from the one in the development environment. Maybe some dependencies and libraries are missing. Maybe some configurations are different. Maybe some system tools are not the same, etc. It is tedious to properly set up a new environment, especially for complex applications. Containerization comes to save the day. So what if we can package an application, in our case, this executable jar file, and everything it needs to run in an isolated unit? This light blue box. So you don't need to rely on what is installed in the production environment. This isolated unit is called a container. We just containerized a Java application. When you deploy your application into any environment, for example, various cloud providers or even on-premises servers, you provide the entire container, this light blue box, instead of just the application, the jar, and you know your code will run. In summary, a container is an isolated environment where an application runs without affecting its environment and without the environment impacting the application. Now, let's zoom into this production server and see how it supports containers. Now we're in the production server. On top of the hardware, we have the host operating system installed. To run containers, we need to install something called Container Engine. This container engine is responsible for running multiple containers on a single operating system kernel. In this tutorial, we will use a container engine provided by Docker. As you can see here, with containerization technology, we can easily run multiple applications on the same physical production server. We can add our new container, this one, to it. You may wonder, why not just use virtual machines or VMs? The containers and VMs have a similar purpose, but instead of virtualizing the hardware, like what the VMs are doing, containers only virtualize the operating system. Containers share the kernel with the host operating system. But don't worry, we're using some features like control groups and namespaces of the Linux kernel to provide isolation among the containers. The footprint with containers is very small compared with VMs. We can run more containers than VMs on a production machine. So containerization really becomes the mainstream now. As you know, Java is famous for its compile once, run anywhere capability. I want to expand it to the deployment context. Containerize once, run anywhere. The application only depends on the container that contains it. It doesn't really matter which production environment runs the container. Well, the benefit of using containers may not be obvious in our monolithic Hogwarts Artifacts Online project, but containerization makes it easy to build and run distributed microservices. Oh, by the way, the term container is borrowed from the shipping containers from the shipping industry. Docker is a containerization platform that helps create, deploy, and run containers. The other popular one is called Podman. Next, let's package our Spring Boot application into a Docker container and run it on the Docker Container Engine. Well, to create a container, we need the container image first. So what is that? A Docker image is a read-only template that defines a container. A Docker container is an instantiated or running Docker image. Many beginners often confuse Docker images with Docker containers. The main difference is that an image is a template that defines how a container will be realized, while a container is a runtime instance of an image. Here is a good analogy that helps you understand images and containers. Think of an image as a Java class, and think of a container as an instance of that class. You can create several containers from the same image. Alright, let's create an image for our Spring Boot application. I assume that you have already installed Docker Desktop on your computer. If not, you need to install that first and make sure it is running. Let's go to IntelliJ. To build a Docker image, we need to provide a recipe with detailed instructions to Docker. That recipe is called Dockerfile. A Dockerfile contains the instructions to create a Docker image. So let's create a Dockerfile in our Spring Boot project. But first, let's create a branch called Containerization. Git branch. Git switch. Make sure the Docker file is created at the top level of your project. I have already copied the instructions. Paste. And you can find the instructions in the description of this video. Wow, this Docker file looks a little daunting. There are many instructions used to build the container image. Don't worry, let's go back to the slides to learn the logic behind those instructions, and then we will go over every instruction. A while ago, I said we need to package the executable jar file produced by Spring Boot into a Docker container, like this. It works. But it turns out that simply dumping the entire jar file inside a container is not best practice. There's always a certain amount of overhead when running an executable jar directly. And in a Docker container, this can be noticeable. It is generally best to extract this jar first and then run it inside a container. So here is what we're going to do instead. First, let's extract the executable jar file and allocate its classes and jars into different layers or directories. This is done by this command. Please note, this command is to launch this jar with a layer tools jarmode. That is, it extracts the 4 layers from the Hogwarts Artifacts Online 0.0.1 snapshot.jar for image creation. It is not running the application. So let me demo this to you. Okay, now I'm under the extracted directory. Let's see what this command will do. Press Enter. Okay, this command successfully extracted the 4 layers from this jar file. Then how does Spring Boot know how to split the application into layers? Recall that there is a layers.index file in the executable jar file, and it contains layer information which separates parts of the application based on how likely they are to change between application builds. This layer information is used to extract the jar contents into a directory for each layer. For example, all the application classes are stored under application. All dependencies are stored under dependencies. And in our case, this folder is empty. And everything under org Spring Framework boot loader is stored under Spring Boot loader layer or directory. Okay, let's go back to the slides. After extraction, we can containerize the application. And remember, extracting the jar and splitting the application into layers is the best practice when containerizing a Spring Boot application. Okay, understanding this logic, let's go back to IntelliJ and look at the Dockerfile instructions again. This is a multi-stage Dockerfile. Here, we defined two build stages because there are two from instructions. The first stage is named as builder, and the purpose of this stage is to extract the layers, dependencies, Spring Boot loader, snapshot dependencies, and application from the executable jar file using this long Java command. In the second stage, we copied the 4 layers extracted by the first stage to the container. The entry point instruction is used to configure the executable that will always run after the image is instantiated. In other words, the entry point command tells Docker to run the jar launcher class when the container starts. Remember, you saw the jar launcher class in meta-info/manifest.mf file. This will cause the Spring Boot loader to start the application. Note that it is the second build stage that creates the final Docker image. The benefit of using multi-stage Dockerfile is to create a final image with a smaller footprint, containing only what's needed to run the application. In the end, we also expose port 8080. Let's look at some details in the first build stage. The from instruction specifies the parent image or base image from which we're building. In this case, we start by pulling the official Eclipse Tamarin 17 JRE image from the Docker Hub, which is a public registry of container images. We then set the container's working directory to application. Here, we assume that the executable jar file is already created and is available under the target directory, like here. The arg instruction defines a variable called jar_file and then assigns the path of the executable jar file, in this case, target/**jar to it. Here, we hard-coded the jar location since we know we're using Maven. If you're using Gradle as the build tool of your Spring Boot application, you need to change this. Next, on line 4, we copy that jar file into the container and rename it to application.jar, since the original name is just too long. Then we're running a script to extract layers from the executable jar file based on the layers.index file. In this example, 4 layers are extracted. They are dependencies, which contains regular released dependencies, Spring Boot loader, which contains everything under org Spring Framework boot loader, snapshot dependencies, which contains snapshot dependencies, in this case is empty, and application, which contains application classes and resources. As I said before, you can think of a layer as a folder with many Java classes and jars. In the second build stage, we're preparing the final Docker image. From a base image, Eclipse Tamarin 17 JRE, then set the work directory. The 4 copy --from commands copy the 4 layers extracted from the first stage to the current image. By the way, a Docker image is composed of multiple layers stacked on top of each other. Each instruction here in the Dockerfile represents a layer in the final image. So in this final image prepared by the second stage, there are a total of 7 layers. The order of the layers is very important. So line 9 to 12 add the 4 layers extracted from the first build stage to the Docker image in this order: dependencies, Spring Boot loader, snapshot dependencies, and application. This layering is designed to separate code based on how likely it is to change between application builds. We all know that library code is less likely to change between builds, so it is placed in its own layer to allow Docker to reuse the layers from cache. I will show you an example later on. Application code is more likely to change between builds, so it is isolated in a separate layer. Content that is least likely to change should be added first, followed by layers that are more likely to change. Please remember this rule when you build a Docker image for an application. Since we extracted the executable jar, we need to explicitly invoke the jar launcher to start the Spring Boot application in the container. That's line 13. All right, that's the Dockerfile, the recipe for building a container image. Next, let's build this Docker image. Let me open the terminal. The Docker image can be built with this command: docker build -t, that's tag, tcu/Hogwarts artifacts online, :1.0, that's version 1.0, space, dot. So don't miss the dot. The dot here means current directory. So the docker build command builds Docker images from a Docker file. In this command, we tag this image as tcu/Hogwarts-artifacts-online with the tag version 1.0. tcu/Hogwarts-artifacts-online is the repository name, and 1.0 is the tag for this image. So this Docker repository is a collection of different Docker images with the same name, but have different tags. At this moment, let's create the first image in this repository. Now remember, don't forget the last dot. That's the path. It indicates the current directory. One last thing before I hit enter. Make sure that this jar file is already generated. That is, we have this target directory first. Okay, notice all that. Let's press enter and build the image. All right, the build is done. And if I scroll up, the Docker build took 15.2 seconds. Well, it's pretty long, right? Okay. As you can see here, the log specifies the detailed building process. It's consistent with our Dockerfile. All right. So let me clean. And let's look at this Docker image. Docker images. As you can see, this is the image we just created. And look at the size. It's more than 300 megabytes. It is pretty large. Why? Because it contains everything. All the dependencies that our application needs. All the jars, launchers, and even a Tomcat server. Next, let's rebuild this image. Keep this in mind. The first build took 15.2 seconds. Do it again. We didn't change anything to the application. We just rebuilt. Wow, this time is much faster. So if I scroll up, as you can see, this rebuild only took 0.6 seconds. Why? Let's look at the log. When you look at the log, you can find a lot of cached layers. This is what's going on. When you run a Docker build, Docker attempts to reuse layers from earlier builds. In our case, from the very first build. If a layer of an image is unchanged, then Docker picks it up from the build cache. If a layer has changed since the last build, that layer and all layers that follow must be rebuilt. We know that in most cases, the application's dependencies and the Spring Boot loaders rarely change between Docker builds, right? So Docker can just reuse the cached results without rebuilding them. This greatly speeds up the Docker build process. What a great idea. To verify what I just said, next, let's modify the application code and build the image again. So for example, we can go to src, main, Java, and for example, go to system, database initializer, and let's change the name of the first artifact from deluminator to deluminator modified. And save. And then let's build the image again. But remember, before we do that, we need to use Maven to package our application. So let's go to terminal. Maven wrapper, package, -d, skip, tests. Okay, great. Now we have a new jar file. And let's run the build command again. Well, it took a little longer, but still pretty fast. If I scroll up, this time the Docker image build took 2.3 seconds. Not too bad. If you look carefully in the log, this Docker image build reused a lot of the cached layers. Only the application layer is rebuilt because we changed the application code. Okay, I hope now you realize the importance of extracting a jar and allocating its classes and jars to different layers. Next, let's bring this image to life. Let's instantiate this image, and here is the command. Docker run -d -p 8080:8080 tcu Hogwarts artifacts online :1.0. Here, option -d means run container in the background and print the container ID. -p means publish. Publish a container's ports to the host. Now remember, the container is running on top of the host. In this command, we bind port 8080 of the container to TCP port 8080 on the host machine. So the first 8080 is the port on the host machine, in this case, my Mac, and the second 8080 is the port of the container. Press enter. All right, as you can see, this one prints the ID of the container. And let's verify the container is up. So first, Docker PS, or you can use this option called -a. -a means show both running and stopped containers. Without -a, Docker PS shows just running containers. As you can see, here we have the container ID, image, command, created, status, ports, and names. There's only one container that is running. All right, then let's verify it in the browser. Let's toggle over to Chrome. So here we have the localhost 8080, API v1, artifacts. So return. Great, it's working. Now, I want you to realize that we're accessing a Spring Boot application within a Docker container. And of course, in this case, this Docker container is running on top of my Mac. How do we stop a container? That's easy. So Docker stop, and just copy and paste the ID of the container. And when you copy, you don't have to copy the entire ID, maybe just the first few characters. So copy this and paste here. So it is stopped. And if you run docker ps-a again, it is still there, but the status is exited 7 seconds ago. So let's go to Chrome and try to access this API endpoint again. It's no longer working. And of course, we can start a stopped container. So here's the command, docker start. And similarly, let's copy this, the ID, paste it here, and press enter. And it's started. Okay, so let's go back to Chrome and access this endpoint again. So it's not showing anything. Well, remember, it takes some time for the Docker to start the Spring Boot application. So the start is not really instant. Okay, but as you can see now, it is working. All right, we're done. Next, let's commit and push the changes to GitHub. But first, let me change this back. We're going to reset the name to Deluminator. We don't want to change that. So close. Git add and git commit m message. Add a Dockerfile to the project so that we can containerize the application. Okay. And then git push. And let's create this branch on the remote repository. All right. Next, let's go to GitHub. As you can see, the new branch, Containerization, had recent pushes less than a minute ago. Let's compare and create a pull request. And this is the file we added. Okay, then create pull request. Okay, cool. And remember, you should really have reviewers to review your new commits. Okay, then in this case, I'm just going to merge pull request. Confirm merge. Let's go to code. And as you can see here, we have the Dockerfile. All right, let's go back to IntelliJ. Let's switch to main branch. And git pull. All right. And we're done. In conclusion, in this video, we successfully created a Docker image for our Spring Boot application manually and ran the container in Docker. It is easily possible to package a Spring Boot fat jar as a Docker image like Approach 1. However, there are various downsides to copying and running the fat jar as is in the Docker image. There's always a certain amount of overhead when running a fat jar without unpacking it. And in a containerized environment, this can be noticeable. The other issue is that putting the application's code and all its dependencies in one layer in the image makes Docker image build slow, since you probably recompile your code more often than you upgrade the versions of Spring Boot you use or a particular library. It is often better to separate things a bit more. If you put the library jar files in the layer before your application classes, Docker often only needs to change the very bottom layer, can pick others up from its cache. Okay, hopefully now you know what is the best practice to containerize a Spring Boot application. In the next video, let's work on deployment. See you in the next video.